Hello and welcome to the wolfSSL live webinar, wolfSentry, presented by wolfSSL Senior Engineer Daniel Posner. My name is Kristen and I will be moderating the webinar. All attendees will be in listen-only mode. If you have any questions, please use the Q&A box or raise your hand to be unmuted if you'd like to ask the question live. We will host a Q&A session following the presentation. The webinar will also be recorded and made available on our YouTube channel shortly after the presentation. I invite you to follow us at Twitter at wolfSSL, as well as our other socials, so feel free to email us if you have any additional questions. And now I'd just like to give a brief company overview before we move on to the technical presentation. wolfSSL was founded in 2004 by Todd Auska and Larry Stefanik when they realized there wasn't an open source dual licensed SSL library available. OpenSSL existed at the time, but there was a demand for an alternative that was easily portable, smaller, faster, available under a clear commercial license, was equipped with a clean and modern API, and offered commercial style developer support. wolfSSL was born into this market need with an OpenSSL compatibility layer. Today, wolfSSL secures over 2 billion connections. We have more than 1,000 OEM customers and dozens of resellers. wolfSSL is made up of over 50 dedicated employees, most of which are engineers. This progress is, of course, supported by our strong partner network. Since the beginning, our engineering team has developed several embedded security products, including wolfCrypt with DO-178 support, FIPS certification, and FIPS ready offering, MQTT up to the v5 specification, SSH v2, TPM2, secure bootloader, as well as Java wrappers and JSSE support, and commercial support for curl. All these offerings are accompanied by a thorough maintenance and support plans up to the 24/7 level. We also offer full service consulting. And now I'd like to turn it over to Daniel to talk about wolfSentry.
All right, thank you, Kristen. So we're going to do both an introduction to what wolfSentry is and how it works, and also an update on the recently added functionalities in wolfSentry. We've added an awful lot in 2023, and I, for one, am pretty excited about it. So in a nutshell, wolfSentry, it is a firewall facility. It's written in pure C. It's super portable. It can target POSIX. We've done a Mac OS X port as just for convenience and as a POC. And we also natively support FreeRTOS with NuLib Nano, which is obviously a production-oriented port that's being used by customers now. And that extreme portability is one of the, it's something common to all wolfSSL products, and it's something that was designed in from the start with wolfSentry, assuring that any architecture or target specific back-end functionality was abstracted so that it would be very easy for us to port to any new target. And we've already done DOS, FreeRTOS, Linux, and other POSIX targets, Mac OS X, and I think one of my coworkers has done one or two others, but the number has gotten large enough now that it's getting tricky to keep track of. Probably a good problem to have. We have native fine-grained IP stack integration now with LWIP. It's done using a single patch set that you just apply to the LWIP 2.1.3, and that adds in all of the hooks that are needed to do fine-grained firewall functionality at all of the relevant OSI layers. And I'll talk more about that later. The configuration is by JSON, and later in the slide deck, I'll show some examples of what that JSON looks like. Or you can use the native C API, or you can arbitrarily mix the two in any combination. And the interface is transactional, thread safe, and I'll explain more about that later. The rules can be dynamically route table rules. In wolfSentry, a rule is actually called a route because they actually, as you'll see, they look like routes. Those can be dynamically generated according to a policy that you can actually update in the field. And you can extend the capabilities of wolfSentry essentially arbitrarily using app-specific plugins, and that's what makes it an IDPS instead of just a firewall. So a little bit about the way the firewall facility works. Rather than having a list of rules that all need to be evaluated until completion, the way a conventional firewall works, wolfSentry has a table of lookupable entries that it creates multiple advantages for us. Because what we're oriented toward with wolfSentry is deeply embedded resource-constrained environments, we wanted to make certain that we were able to evaluate new traffic and keep track of peers that we need to keep track of with a minimal resource footprint. And one of the ways that we did that was by having a model of the address space where a particular peer will have a single representation in the table, and the lookup in order to evaluate new traffic involves just looking up in a single table rather than going through a whole list of rules. That results in eventually a hard guarantee of login performance for evaluating any given traffic event. So in this table, this internal representation of the address space, the sort key has the address family leftmost, which is an obvious thing to do because there's no interaction between different address families. And then it has the remote address. When you're trying to put an adversarial peer in a penalty box and ignore traffic from it in a very efficient way, the most important thing to be aware of is the remote address that you're putting in the penalty box. So we put that first in the lookup table, and that results in optimal efficiency for looking up a given remote peer. So if we're tracking a remote peer, then we get that guarantee of the login lookup of that adversarial peer. Followed by following the remote address, we have the protocol, the local port, and the rest of the network traffic attributes, and then finally priority. And the role of the priority is so that you can put in rules or routes that have override priority. Whichever match in the route table has the highest priority is the one that takes precedence. That's the purpose of having a priority. And that gives you very predictable dynamics in terms of designing your policy. So as I said, the idea is that by putting the remote address first, the classification needed for an adversarial peer is the lookup that's most efficient, and those are the peers that are most likely to be generating huge amounts of traffic that need to be efficiently ignored. Oh, and of course, prefix matching is fully supported. Wildcard matching in any of the fields is also fully supported, and it does that efficiently. If you so we're constructing a sort key here, and if you wildcard the route table entry so that the first several fields are all defined and then the rest are wildcards, it's able to do prefix matching on the overall sort key, and you maintain optimal efficiency. If you have holes in your wildcard configuration, there is a reduction in efficiency, but those are unusual cases that aren't likely to be performance sensitive anyway. So beyond being a firewall, wolfSentry can also be the core of an embeddable IDPS. So an IDPS, the idea is to have network visibility into the type of traffic that's going on, the type of events that your infrastructure is seeing. wolfSentry is not an infrastructural IDPS, it's an endpoint IDPS. And the idea is that it facilitates instrumenting, using it as an implicit agent on your endpoint that's integrated into your application and into your IP stack. So because it has a dynamic firewall facility, you can deal efficiently with various threat patterns, and I'll talk about that and show some configuration around that later. But even more relevant to the IDPS use case, it allows for very tight integration with libraries like wolfSSL. And in that case, the integration means that if you have a peer that is spamming your endpoint with cryptographic negotiation attempts, the application logic, the library logic knows that. And wolfSentry as an IDPS allows you to leverage that using simple call-ins. And I'll talk more about that in later slides. But the general idea is that the application and its existing libraries already have the knowledge, already have the logical expertise to classify traffic patterns into friendly or adversarial. And wolfSentry makes it very easy to leverage that without increasing your footprint size. So on the inside, as I was describing, wolfSentry is like a database. The reconfiguration has atomic semantics. A new configuration can be loaded at any time during runtime dynamically. And it's built alongside and parallel with the running configuration without disrupting the running configuration. And if and only if the evaluation of the new configuration succeeds, which includes full self-consistent syntax, self-consistency checks, then the new configuration takes effect and the old one is deallocated. The configuration can be done programmatically in C or C++ using the API or by JSON. And we maintain a firm abstraction barrier between the two to assure that the JSON capabilities any capabilities in the JSON are fully available to an application. You don't have to violate any abstraction barriers in order to get full semantic access to wolfSentry's full capabilities. And another of our optimizations in order to make wolfSentry be optimally compatible with deeply embedded resource-constrained environments is that we use a fully streaming a configuration evaluation architecture. It's called SACS. And what that means is that you can feed the JSON configuration into wolfSentry in blocks of as small as you want. You could do it in 512 byte pieces. And the wolfSentry core will evaluate it progressively without having to store up an intermediate representation. And that minimizes the amount of internal resources used for the reconfiguration process. So here's I mentioned this at the outset, and now we'll go through it in a little bit more detail. The code base can be built in a fully C89 compatible mode. We've done the Linux POSIX port that was for convenience's sake as a developer aid, and then we did Mac OS X as a proof of concept and also for developer convenience. The most mature production relevant port that we've done is FreeRTOS with NewLib Nano and LWIP. And we fully support all of the native intrinsics, and that's in production now. And as I said, it's LWIP 2.1.3 is what the patch set applies to. We've actually been able to apply it to 2.1.2 also. So as long as you're using LWIP from 2017 sort of time frame or later, the patch set will apply cleanly. And it also applies cleanly to the head of master in LWIP. And that patch set adds in the LWIP intrinsics to do fine-grained filtration at all OSI layers. And you have fine-grained control at layer 4 of traffic, of ICMP, TCP, and UDP traffic. And another pretty significant value add with the LWIP integration is that we pass the LWIP integration passes a pointer to the full packet with its headers to wolfSentry, and then wolfSentry plugins have full access to the raw packet. So if you have a need to do some sort of deep packet inspection, that's trivial to add in. with full application specificity. We've also done a proof of concept filtering CAN bus traffic. And that's one of the things that's important to recognize about wolfSentry is internally, it's not wedded to any particular address family or even even network model. It works with a UART. You could do I2C or CAN bus as in this POC, and it's perfectly relevant because the addresses are done using just bit matching, prefix matching of bit strings. So here's an overview of what we've added over the last year or so. We've added in user-defined key value pairs. These are useful particularly for application-specific plugins where you need to configure them in some sort of application-specific way, and it allows you to put that configuration into the unified JSON configuration and then distribute it as a single JSON object. And that also includes full free-form, deep tree, user-defined JSON values. We also allow, as I implied, fully user-defined address families. And these allow you to, that means that not only can you support things like CAN bus using idiomatic address representations, but you can do full support using idiomatic representations of proprietary buses and proprietary address formats. And it's all very streamlined and easy to use. And it is automatically integrated into the JSON parsing mechanism and the JSON production mechanism that I'll get to in a second. There are JSON helper routines that are optionally built into the library that make it easy to manipulate JSON to access leaves in a JSON tree wherever they may be, including in the user-defined JSON trees. That's just a convenience feature, but it means that you have full JSON processing capabilities just by bringing wolfSentry in, and you don't have to bring in your own JSON processing library to do it. There's now automatic penalty boxing logic built in based on keeping counts of how many derogatory events a particular peer has run up. And we have an example application bundled with the release that includes dynamic rule generation and dynamic real-time notifications of over-the-wire events. Okay, so I said that there's JSON dump. This is a very recent addition earlier this year. It's now possible to checkpoint the current the current policy in the route table by exporting it as JSON, and it's exported naturally in a syntax that allows you to reload it at a later time into the wolfSentry engine. And that allows you to do shutdown checkpointing, and then at the next boot, you can reestablish the exact policy configuration that had been dynamically established as of the most recent shutdown. We have new dynamic rule generation capability using built-ins that allow you to, for example, dynamically open a pinhole to access a DNS server over UDP, which is it's a connectionless protocol, so that makes it somewhat trickier to support it. You need dynamic rules, you need a stateful firewall to do it, and that's now a turnkey built-in capability, and I'll actually show the configuration to do it later in the slide deck. And we also now include all of the capabilities for built-in port scanner detection and dynamic blocking. All of the public APIs in wolfSentry now have auto locking. So because internally wolfSentry is a database, it's very important, and because it's thread safe, it's very important that locks be appropriately obtained and checked for all of these internal transactions. That's now all done implicitly. When you make an API call into wolfSentry, you don't have to think about that. It's all handled automatically. That's true in POSIX targets, and it's true in FreeRTOS natively. So one of the things that's become clear over the last couple years of the initial development push for wolfSentry is that the use cases where wolfSentry is a good match are where you have a deeply embedded target that wouldn't otherwise have any firewall at all. So anywhere where you're using LWIP or an LWIP-like IP stack, one of these very lean embedded IP stacks, you don't actually have a firewall because these IP stacks don't support firewalls. Our patch set for LWIP adds that capability in, and when you pair it with wolfSentry, you get a full turnkey, dynamically reconfigurable firewall facility in these deeply embedded targets. The best way to think about wolfSentry in practice is that it is a firewall. It's adding a firewall to places that didn't previously have firewalls, but its plugin capabilities allow it to be extended arbitrarily. And I'll talk about what our plans are for additional built-ins later in the slide deck. So another lesson learned is that in environments, so it's very common these days to have these heterogeneous environments where you have some sort of hub, like a supervisory hub that's running embedded Linux. And wolfSentry is not a very good match for embedded Linux for the simple reason that Linux already has powerful firewall facilities. Now, in many cases, that firewall facility is probably too powerful. I'm thinking of IP tables. And we will eventually get around to porting wolfSentry to the Linux kernel. But for the time being, our general recommendation is to think of wolfSentry as a way to add firewall capabilities to protect deeply embedded endpoints and interface with Linux only at the level of sending notifications to it, for example. So an architecture built around that sort of notion has Linux on the outside, and then an inner sanctum running some sort of RTOS that has wolfSentry integrated with it, so that your inner sanctum has its own full security perimeter that it's enforcing. It's no longer depending on the very complicated, much heavier Linux ecosystem to provide all of its security. And that's layered security. That's sort of best industry practice. So a look at the type of threats that we have in mind with wolfSentry. The assumption is, of course, that you have cryptography-based security already in place, so that you don't have brute forceable surfaces. Your main concern is quality of service attacks, denial of service attacks. That said, if you do have a need for any sort of password-based protections, wolfSentry is doubly relevant to your use case. So public key operations are expensive, and that is extra true on deeply embedded targets. Deeply embedded targets sometimes can take more than a second to perform some of the public key operations needed in order to negotiate a new session. And that means that if your endpoint, if your deeply embedded endpoint is exposed on an insecure network, it becomes subject to a pretty devastating denial of service attack. It can wind up having all of its resources used up just servicing bogus negotiation attempts. So the idea is to detect those bad negotiation attempts and then dynamically block the peers that are attempting to do that. And wolfSentry makes that very easy. And the bundled notification example that comes with the wolfSentry release actually implements that exact type of protection. It detects when a crypto negotiation was not successfully completed. It's a mutual authentication use case. And each time it's attempted but not successfully completed, the derogatory count for that peer is incremented. And when it gets to a certain number, in this case 5, it dynamically blocks it for a period of time. So this slide just calls out the details of that use case, where your adversarial peer is bombarding you with bad connections, and you want to be able to ignore that adversary with minimum cost. And wolfSentry makes that very easy to do. So this is just a quick look at the architecture of wolfSentry. The best way to think of it is it's as a database and a central logic hub, and it allows you to tie together multiple modules in your application, and then relate them to each other with a policy that you can dynamically update. And in cybersecurity, it's very important to be able to adapt to threats as they evolve, and that's one of the key capabilities of wolfSentry. It doesn't require that you recompile in order to change the dynamics of your system. You just have to load a new configuration, and you can do that in the field. And if you develop your application to allow it, you can actually make it possible even for a field technician to add to the running configuration in the firewall. So it's not just not having to recompile, it's you don't even have to restart your endpoint. You can do it fully dynamically, and your application continues to run with no gap in service at all. There are three main object types in wolfSentry: routes, which are typically called rules, but they look like routes in wolfSentry, and they're fully dynamic, and you can specify them either with JSON or using the C API. Then we have this concept we call an event. It's like a filter definition in fail to ban. It allows you to organize your policy around these ideas of when there's a connection, I want to do something. When a transaction fails, I want to do something. When a handshake fails, I want to do something. And those are also dynamically definable, and you can add them or remove them using either JSON or the C API. And then finally, we have actions themselves. These need to be installed by the application. They're written in C, and then they get names. You can change the names of them at runtime, but you can't change the logic behind them because they're written in C. So the flexibility of that mapping between events and actions is where a lot of the power of the system comes from. And that's fully configurable, reconfigurable at runtime. So when you do, and so you don't have to do, so here I'm talking about application integration. You don't have to do any application integration to use wolfSentry now, because wolfSentry is fully integrated into the LWIP stack. And that means that you can just use it like an operating system supplied firewall. You just initialize when your application starts up, and then you don't have to think about firewalling if you don't want to. But the system is far more powerful if you add in some application integration so that wolfSentry knows when a peer is acting in an adversarial way. Some of as I said earlier, some of the types of traffic that an adversary supplies are classified as such by your application already. And by just adding in a simple single line call-in to wolfSentry when a bad or good event happens for a given peer, wolfSentry gains that knowledge that the application already knows. So that would be like, obviously, bad password would be an example of an adversarial event that you could pass into wolfSentry. And then if someone has 5 or 10 bad passwords in a row, you would ignore that peer for some period of time. And the application can register a callback for any event label, just like it can register any action. And that's what facilitates inter-module coordination, because you can have different parts of your application registering different callbacks, and then you can maintain your own abstraction barriers, and you're just registering the callbacks from within each of the modules. So right now, the internal tables are just using ordered lists in order to do the lookups. The amount of state that's currently being traversed is small enough that that's not a meaningful impact. But for certain, particularly distributed denial of service attacks, it will become meaningful to use a B-tree type lookup internally, particularly in the route table. So that's something that's on our roadmap, to update that to use B-tree type lookups. As I said earlier, the addresses are all generic bit vectors, and that means that they can support any address family where prefix-based bit matching is relevant, and they can do so efficiently. The allocator and time functions are completely abstracted, so a user with a different strategy for those contracts can supply their own routines to do it. And we have pretty robust management of the memory footprint, the resource and memory footprint internally, including fully deadline scheduling. You can, in a deadline scheduled multi-threaded target, you can set the time that wolfSentry needs to return by, and wolfSentry will always return by that time, either with I ran out of time to make a determination, or having completed it, but it will not lock up the system for longer than you tell it it's allowed to lock up the system for, in order to facilitate deadline scheduled real-time, hard real-time environments. One of the things that's also on our roadmap is its compactification of, so some denial of service attacks involve many addresses from the same net block launching attacks. And in that case, you don't want to waste resources tracking each of the individual fully specified addresses separately. Instead, you want to pool them together. And one of the things on a roadmap, and there's actually some infrastructure in the code base already to do this, is automating that capability. So the latest in 2023 is we've just put out the 1.4.1 release. The native integration with LWIP is also a 2023 edition. The dumping of the route table configuration to JSON that can later be re-ingested is a recent addition. We've added, with the 1.4 release, we added in the a built-in action, the first built-in action, one of many to come. And this is just for tracking peers. And I'm going to show a demonstration of that in a second with a demonstration configuration. And we've also added in some very powerful filtering and setting and clearing of bits that you can now associate with event configurations. And you can see that there, and I'm going to show them on the next several slides. So here is, and this is an example. It's a configuration fragment that shows how to actually dynamically open a pinhole route to a DNS server in order to allow DNS replies to reach your application in a configuration that has a default deny policy. So the first thing to look at is this is adding events to the system, and this here is going to be the parent event for all of the dynamically inserted rules that allow the reply, the UDP DNS reply, to reach it. And it will be garbage collected from the system after just 10 seconds in this configuration. And it's set up to apply to the inward and outward traffic. And of course, it's green listed, which means that it's implicitly accepted. And it has a very high priority because we want it to take precedence over any other rules in the system. This is the event for setting that up in the first place. And as you can see right here, it refers to the first event. And the way the configuration looks, conceptually it's a little bit backwards. The main magic is here. You add in a route, it's a rule that is expecting outbound. So it's looking at outward traffic, it's ignoring inward traffic, and it's always allowing outbound port 53 UDP traffic. And when it sees that, it's going to follow the directives associated with this event. So the parent event of this route is this pinhole generator parent. And if we go back to look at pinhole generator parent, we can see that it's going to, these are for testing purposes, but it's demonstrating how to clear and set various bits and how to filter on them. Here, it's going to call the built-in action that's going to create the pinhole route. And the new parent for the pinhole route is specified with the auxiliary parent event, which is this. The first thing in the configuration that has the temporary lifespan to it, and the constraint on matching all inbound and outbound traffic and implicitly accepting it. So here's just a quick look at the type of stuff that we're looking at for the near future in wolfSentry development. We're looking at adding in a built-in action that allows you to send out a syslog message for traffic events, and that will include a full DTLS capability. So you can cryptographically secure the notifications using industry standard protocols for the whole stack. There will be comprehensive documentation for everything that I've talked about above. There will be some turnkey. So obviously this is test configuration, but we will actually be bundling some turnkey JSON configurations that give you these capabilities without having to dive into the details. There will be more ports, and there will be more IP stack integrations. And with that, I will stop and wait for questions.
If you'd like to ask a question directly, just raise your hand and I'll unmute you. There doesn't seem to be any questions.
It's because I spoke too quickly.
It's because you spoke very thoroughly.
Kristen, did my presentation raise any questions for you?
Looks like here's a question.
Okay.
Is syslog messaging being implemented on other stacks as well?
The syslog messaging will be using native capabilities in wolfSentry. So that will be a pure C implementation. It will leverage wolfcrypt and wolfSSL for the DTLS encapsulation. So that will be usable on all targets. That'll be architecture independent. We'll go back to this slide.
Daniel, maybe you can tell us about the latest release that you just released today and how quickly that was a turnaround.
Well, actually, the latest release was yesterday.
Okay, yes.
1.4.0 was yesterday. 1.4.1 was today because of a portability issue turned up by nightly testing. And that's neither here nor there, but the new capabilities in 1.4.0 are these the built-in action handler here, and all of this the filtration and clearing and setting of these bits that you can see like here. And I mean, the advantage of with the new capabilities, the 1.4 version 1.4 capabilities, the advantage is that you can now express using fully dynamic and field reconfigurable policy the type of fine-grained traffic evaluation and the like action nuance that previously would have required handcrafted C with a rebuild, and you know, that's a really big deal to be able to update your policy with that much power and flexibility in the field without any recompilation or anything. So all of this stuff that you see here is using the 1.4 capabilities. And here you can see, there's another question.
Yep, yes, there is. Let me know when you're ready.
I am.
Okay, we are currently using STM32H7 based microcontrollers for our projects. Is there a baseline of what kind of performance we could expect on similar microcontrollers, or should we use a more powerful types of controllers to utilize wolfSentry?
wolfSentry has almost no impact on performance at all. It was designed from the ground up to use no more CPU cycles than necessary. It's very unlikely that you would even notice it. The only thing that you would have to think about would be footprint size, and there are build configuration options in wolfSentry to cut down the footprint size to under 100K. If you build it with all the bells and whistles, it's going to be 200 to 300K probably. But if you're footprint constrained and you don't need the fancy stuff, then you can just switch off all those capabilities and get a very cut down build. And in terms of CPU cycles, especially if you're on a single threaded target, and a lot of LWIP targets are, LWIP is itself single threaded. You probably won't be able to measure the impact of wolfSentry. It's just so efficiently implemented internally. So I was going to call out these are user flags. So throughout wolfSentry, there's just a general philosophy that we can't think of everything and we shouldn't try. So everything is extensible. If there's some semantic that you want to support, you can support it using actions of your own definition, events of your own description, and also bits that your application passes in and then gets back out of your own. There's, for example, 8 bits that are user defined for the action result. That's the main output from the dispatch that is used in order to classify traffic.
The FIPS module uses specialized linker scripts for the runtime checks. Are there similar issues with specialized linker scripts when using wolfSentry, or can wolfSentry be used as a static library?
It's fine as a static library. There's no cryptography in wolfSentry, so you don't have to think about FIPS. Those are if you have wolfcrypt in your image, that's a completely separate part of your image that doesn't interact with wolfSentry directly.
Is there an STM32 package that fits into STM32Cube MX?
There is, but it hasn't been updated in over a year, so it would probably need some fixing before it would be ready to go. But we have certainly done it.
Okay, well, if there's no more questions, Daniel, thanks for the presentation, and participants, thanks everyone for joining. We'll follow up with a link to the recording and the presentation, and please let us know if you have any questions. We're happy to schedule a meeting to discuss in more depth. Thanks, everybody.
Thank you, Kristen.
Thank you. Bye-bye.